So good evening, everyone. Welcome to day 3 of the FDP AI Agents in Action. Today we have our speaker, Harshavardhan sir. You know him very well as he has a very good session in the last day. So our today's schedule. I request everyone, please mute your mics. Harsha sir is with us. Our day 3 schedule is you are going to learn about the learning agents and autonomous behavior of them and what the learning agents are and what are the basics of reinforcement learning and multi-agent systems and handling uncertainty in environments. So these are the topics which are going to be covered by Harsha sir. So I welcome Harsha sir for the day 3 of the FDP and I'm handovering the session to him. Harsha sir.
Yeah, ma'am.
Sir, please continue.
Yeah, sure. So, good evening, everyone. So, I'll just introduce myself again. I'm Harsha. I'll be taking the session where we learn something called as learning agents and autonomous behavior of learning agents. So, we'll just start the session. And until now, whenever we discussed intelligent systems or agents, we usually assume that intelligent systems or intelligence is something we design and embed into a system, or intelligence is something that we just put into a system. And we write the rules, we write the logics, we write the conditions, and we write all the decision trees that the model has to perform. And we expect the system to behave intelligently. Yeah. So that's what we have been assuming since the last 2 days. Today, we move one level deeper. So moving one level deeper means learning how agents really work or learning how agents really think. We just talked yesterday regarding how agents make decisions, and today we'll just see how they learn and how do they behave. So today's discussion is about learning agents, systems where intelligence is not fully predefined. We don't predefine any sort of intelligence, but develops over time through interaction with environment. So this shift is very important because most of the real world environments are not stable. They are not predictable, they are not stable, and neither are they clean. So for these cases, we need an agent or we need something that reacts to environment. So today we'll be talking about all of those agents. So let me just share my screen. Yep. I hope my screen is visible.
I request everyone, please mute the session. If you, mute your mics. And if you have any queries, you can ask sir through chat. Please, I request everyone to mute your mics so that there will not be any disturbance. Thank you very much.
Yeah. So if we are good to go, we'll just start. So firstly, let us start with a simple observation. Yeah, we'll just start with a simple observation where rule-based systems assume that the world behaves as expected, or the outcome will just come as if we expect. But in reality, environments are not like that, or they don't work like that. So environments are uncertain and they are noisy. Yeah. So when we just combine both of them, being uncertain and being noisy, we get a metric called as dynamic. They are both uncertain and they are also noisy. So they are dynamic and also they constantly change. So these are the these are the things that make our environment dynamic and uncertain. So a rule that we define works only as long as the assumption behind it remains. Yeah. So whenever you write a rule or whenever you just write something, you just assume that it should be true in all the cases. The rule only applies if everyone follows it and everyone just follow all those rules without anything like let's say a person does not want to just overrule it or a person does not want to obey the rule. These are things that we don't consider. So for an example, let's just consider a university timetable. Yeah, a university timetable designed purely with fixed rules. A university timetable is always designed and it has fixed rules. It works perfectly until a faculty member is absent. As long as all the faculty are there, it works fine. X faculty takes first period, Y faculty takes the second period, and Z faculty takes the consequent one. So as long as all the faculties are there, it's all great. Let's just say on on a fine day, one of the faculty member has just taken a casual leave, and which means one of the faculty is absent. So what happens over here? A classroom becomes unavailable. Yeah. So a classroom becomes unavailable without a teacher in it, or schedules change unexpectedly, where the Y professor has to take the first session, which he was originally supposed to take the second. But yeah, because of the absence of X, the Y has to push his session forward. Every exception, every exception requires rewriting the rules. Let's say if you just say that no, I won't take the session, you can't do that. You can't leave the students unattended. So you'll have to rewrite the rules and you'll have to attend the first session. And it also needs something called as manual intervention, where a man or a human has to intervene or has to change the rules. And doing all of these will just lead to something called as redesigning the rules. Yeah. So rules do not fail because they are incorrect. Rules are correct. Rules are written so that they are followed and they are correct. But they fail because the world changes. They fail because the world changes faster. It changes faster than the rules can be updated. If the teacher was available, or if the teacher has intimated that I would be not coming on this certain day a month ago, they would have changed the schedule. But yeah, emergencies don't come set. They just pop up. So the world changes. This limitation is the motivation for learning agents. So we'll just get to we'll just get to the part where we'll understand what a learning agent is. So what exactly a learning agent is? A learning agent is an agent that improves its performance over time. That improves its performance over time using feedback from the environment. So it takes the feedback from the environment and try to improve itself. The most important idea over here is it changes. It changes over time. its ideas, its thought process, its ideology, or the actions that it does, they change over time. Yeah. So a reactive or a rule-based agent behaves the same way today or tomorrow. It behaves the same way. Does not matter which day it is, or does not matter what the situation is. It behaves the same way as it has been defined. You write few rules and it just follows all those rules. But yeah, a learning agent behaves differently. A learning agent behaves differently when it comes to a case where tomorrow, let's say today a learning agent has done something. It has just walked 1 kilometer. You can't expect a learning agent to walk the same 1 kilometer tomorrow. It would just either walk 800 meters or it could go 2 kilometers extra. So you can't predict what it is going to do tomorrow. So the difference over here is very fundamental. For example, a paper map. A paper map never changes. Google Maps continuously change. Yeah. So let's say an Indian map or a political map, it does not change. It is just there. It is already pre-written or it is already pre-drawn. But the Google Maps that we use, it continuously updates routes based on traffic conditions. Google
Yeah.
Maps continuously
So
change. Now,
yeah.
we'll just
So
compare, let's
the
say, an
paper
Indian
map.
map or a
Yeah.
political map. It
Let's
does not
say that
change.
paper map is a
It is
rule-based
just there.
agent.
It is
Already
Google map that we generally
pre-written
use.
or it is
Is a
already
learning
pre-drawn.
agent.
So what's the
But
fundamental
the
difference?
Google Maps that we
The
use,
fundamental
it
difference is
continuously
the paper map
updates
does not
routes
change,
based on traffic
but the
conditions.
Google map.
Google
Yeah.
Maps
Or the
continuously
maps that we
so
generally follow,
now
they
yeah,
change
we'll just
based on
compare,
what?
let's
The
say, an
paper
Indian
map,
map or a
real-time
political map.
traffic.
It
Let's
does not
say that
change.
paper map is a
So it is
rule-based
just there.
agent.
Google
It is
Maps is
already
not
pre-written
intelligent.
or it is
Is a
already
Google
pre-drawn.
Maps is not
So what's
intelligent
the
because it
fundamental
knows the
difference?
Google Maps that we
The
use. It
fundamental
is
difference
intelligent because
because the
it
paper map does not
adapts
change
based on
and it
traffic
behaves. But the
conditions.
Google map,
Google Maps
or the
continuously
maps that we
it
generally
adapts.
follow,
Now
they
and it
change
behaves
just
based on
based on
what?
the
Let's
feedback.
say
The
an
paper
Indian
map,
map or a
real-time
political
traffic.
map. Learning
Let's
agents do
say
not
that paper
follow
map is a
so it is
rule-based
just there.
agent.
Google
Google
Maps
Maps
is
they
not
outcomes
intelligent
or they follow the
is a
reasoning.
Google Maps is not
That so what's
intelligent
the
because it
fundamental
knows
difference?
when
The
they complete a task.
fundamental
It is
difference
intelligent because
continuously
the paper
updates
map does not
routes
change
based on
and it
traffic
behaves.
conditions. But the Google
So
map,
Google Maps
or the
continuously
maps
so
that we
it
generally
adapts.
follow,
Now
they
and it
change
behaves
based
based
on
on
what?
what?
The
Let's
feedback.
say
The
an
paper
Indian
map,
map or a
real-time.
political map.
Learning
Learning
agents
agents
do
do
not
not
follow
follow
is a
so it is
rule-based
just there.
agent.
Google
Google
Maps
Maps
is
they
not
outcomes
intelligent
or
because
they
it
follow
knows
the
when
reasoning.
Google Maps is not
That so
intelligent
what's the
because it
fundamental
knows
difference?
when they
The
complete a task.
fundamental
It is
difference
intelligent
is
because
the
the
paper
paper
map
map
does
does
not
not
change
change based on
and it
traffic
behaves.
conditions.
But the Google
Adapts.
map,
Google Maps
or the
continuously
maps
so
that we
it
generally
adapts.
follow,
Now
they
and it
change
behaves just
based
based on
on
what?
what? The
Let's say
feedback. The
an
paper
Indian
map,
map or a political
real-time.
map.
Learning
Learning
agents
agents
do
do
not
not
follow
follow
instructions
so it is
and
just
they
there.
just talk
Google
about
Maps
or
is not
they
intelligent
outcomes or they
because it
follow
knows
the
when
reasoning.
Google Maps is not
That so
intelligent
what's the
because it
fundamental
knows
difference?
when they
The
complete a task.
fundamental
It is
difference
intelligent
is
because
the
the
paper
paper
map
map
does
does
not
not
change
change based on
and it
traffic
behaves.
conditions.
So
So Google Maps
or the
continuously
maps
so
that we
it
generally
adapts.
follow,
Now
they
and it
change
behaves just
based
based
on
on
what?
what?
The
Let's say
feedback. The
an
paper
Indian
map,
map or a political
real-time.
map.
Learning
Learning
agents
agents
do
do
not
not
follow
follow
instructions
so it is just
and
there.
they just talk
Google
about
Maps
or
is not
they outcomes
intelligent
or
because
they
it
follow
knows
the
when
reasoning.
Google Maps is not
That so
intelligent
what's the
because
fundamental
it knows
difference?
when they
The
complete a task.
fundamental
It is
difference
intelligent
is
because the
the
paper
paper
map
map
does
does
not
not
change
change
based on
and it
traffic
behaves.
conditions.
So
Google Maps
or the
continuously
maps
so
that we
it
generally
adapts.
follow,
Now
they
and it
change
behaves just
based
based
on
on
what?
what?
The
Let's say
feedback. The
an
paper
Indian
map,
map or a political map. Learning
real-time.
agents
Learning
do not
agents
follow
follow
so it is just
and
there.
they just talk
Google
about
Maps
or
is not intelligent.
outcomes.
There is an outcome, and the outcome is evaluated. The outcome is evaluated. Based on the evaluation, the agent updates its future behavior. So this is the analogy. Firstly, it performs an action. An action can be as simple as just placing an object from one place to another. We are just placing an object or a glass from one place to another. Yeah. And based on that action, the glass has moved from across the table. It has moved from one side of the table to the other side. And because of this, the table's environment has changed. So we'll just evaluate. We'll just evaluate if the change in the environment is good or not. Let's say you're sitting on the other side of the table. You're sitting on the other side of the table where the glass was not originally there. The glass was not originally there. But yeah, because of the outcome, the glass has moved towards you. The glass has moved towards you. Now the outcome is favorable to you. So favorable outcomes are evaluated and non-favorable outcomes are also evaluated, but we'll just discuss the difference between favorable outcomes and non-favorable outcomes in a few minutes. We'll just get there in a few minutes. But the critical point here is the agent is not told the correct action. Yeah, it is not told the correct action. It could either put there or put here. It is only told how good or bad the result was. Yeah. So if it's good, we just say that it's good. If it's bad, we just say that it's bad. The agent just perceives the result. A yes or no, a zero or one, a good or bad, these sort of things. So when it comes to learning agents, this distinction is very important. Yeah, it is extremely important for learning agents. So as the name suggests, they learn. They learn out of the results that they get. So they just learn things. So we'll just consider an online exam proctoring. Yeah, online exam proctoring. Initially, it may flag many false positives. Yeah, it may flag many false positives, or it may just correct the wrong papers. Based on feedback, based on feedback, it adjusts itself. It adjusts its sensitivity thresholds, and over time, the system improves without rewriting any sort of rules. So the proctoring is based on a rule book. You don't really change the rule book, but you change the way that the proctoring is done. It follows all the rules, but it does not do the mistakes that it has done previously. So here, a point to be noted is the system. The system is not corrected, but the proctoring method or the agent that does the proctoring corrects itself. Yep. So what I really want to sum up is our agent just observes and then takes an action. Based on the action, it receives a feedback. And based on feedback, it will just update its knowledge, saying this is bad, this is good. And based on those good and bad decisions, it will just decide to whether improve its decisions or deteriorate its decisions. So in reinforcement learning, a good or bad are said using rewards. Yep. So a good or bad are decided using rewards. So the rewards could be general zeros or ones, or let's say we'll start with a standard number. We'll start with something called as 10. You have a score of 10. Whenever there's something good, or whenever there is an outcome of good, the reward is plus one. Yes, the reward is plus one. And whenever there is a bad outcome, the reward is minus one. So an AI agent or a reinforcement learning agent would just perceive or improve its decisions based on the rewards that it gets. And each cycle refines the agent's understanding, leading to progressive better performance. Yeah, I hope we are clear with how learning agents internally work. So they just reinforce their own learning and try to be better than they were. Yep. So if you are good till here, we'll just move to something called as adaptive behavior. Yes, we'll just see what adaptive behavior is. So this is an ability to modify behavior based on experience and based on the outcomes or based on the rewards. So it is the ability to modify the behavior or modify the actions. So we'll just get to know what adaptive behavior involves. So adaptive behavior involves something called as trial and error. So trial and error, we all know what trial and error is. We try something, if it's good, it's good. If it's an error, we try it again. So this is a method or this is a cycle. It goes as long as we get the desired outcome that we need. And adaptive behaviors are feedback driven. Yeah. So adaptive behaviors are feedback driven. And what are the things or what are the benefits that we get because of both of these? Because of trial and error and because of long-term improvement. We'll just get something called as, sorry, because of trial and error and because of feedback decisions. We get something called as long-term improvement. The agents improve based on time. And over here, intelligence is not about being correct all the time. The context of intelligence is not being correct all the time. Intelligence is about learning from the mistakes. So, so we'll just know about few examples where learning from mistakes has gotten better. So as you can see on the screen, We have Google Maps dynamic routing. We'll just talk about it. So Google Maps dynamic routing. So what's the cause or what's the problem? Traffic patterns change continuously based on accidents, weathers, events, some etc. things. So this is the problem or this is the cause. So what's the effect? The effect is routes are recalculated. Routes are recalculated in real time using live data from millions of users. We just talked about Google Maps yesterday. So I won't be repeating the same thing again. But yeah, so what's the outcome? The outcome is we get something called as an optimal path or a path with lesser traffic in it. Yes. How does an AI agent achieve that optimal path? So it achieves the optimal path by collecting experience. It just collects all the experiences. We just talked about Bangalore situation yesterday. So that situation will be the same today also. So when the same situation arrives on each and every day, the experience or the behavior of the agent changes based on it. And they are not pre-programmed rules. You can't pre-program that at 6:30 you'll have this much traffic. It is unpredictable. The traffic is unpredictable. And so that's the reason why Google Maps is always dynamic. Yeah. And few more examples are spam filtering. So spam filtering, we all know that we use machine learning for spam filtering. There's this pattern that all the spam messages have, and based on the pattern, the agent just the agent just identifies that this is spam and this is not. So this is another example of spam filtering, or this is another example of adaptive behavior and adaptive proctoring. So adaptive proctoring, we just talked about adaptive proctoring. And what is the pattern over here? The pattern over here is collecting collecting experiences, collecting your experiences all together and recognizing the patterns in them, collecting information, recognizing the patterns, and adjusting based on the outcomes. We get collecting and pattern recognition in machine learning. But in machine learning, we don't have a concept called as adjusting to the environment. This is where learning agents or AI agents have emerged from. Yeah. So the next part is reinforcement learning. So we'll get to the core part of reinforcement learning. And the core concept over here is agent learns optimal behavior from by interacting with the environment. Yeah. So it interacts with the environment and gets to optimal behavior. So what are the things that decide its optimal behavior is they are the rewards that it gets. So the rewards are the signals that guide decision making. So let's say if it gets more rewards, it starts moving or it starts its learning curve towards more rewards. And whenever it receives lesser rewards, it does not go to the side because lesser rewards means it's not going towards its goal or it's not doing its task very well. So we'll just get to the point where it performs poorly because of its decisions. No AI agent performs poorly because of its decisions. It performs poorly because the rewards are wrongly placed. They don't follow the rules. They don't follow anything. They follow their instinct called as getting more rewards. So rewards is the villain over here. And what are the components that we have in reinforcement learning? First one is trial and error. So agents explore different actions. Agent explores different actions based on what? So they just explore different actions based on the environment or based on the strategies that they are going to put in. Yeah. So the agent is never given a correct action. Yep. The correct action is never done by the agent. The agent only does an action out of exploration. Out of exploration, it will just do some action. It could be correct or it could be wrong. So the basic cycle over here is the agent observes the situation, takes an action, and receives a feedback, and hence adjusting its behavior based on the feedback. So this is very similar to how human learn skills. When we learn to ride a bicycle, no one gives us a formula. No one says that putting your body to the left or putting your body to the right will just lead to something called as driving optimally. You try, you fall, you adjust, and eventually you improvise. You make your own style of riding. So reinforcement learning is about learning what works, not what is correct. Yep. So let's say there's this one matrix where everyone has to drive the cycle in a same way. We don't follow those rules. Everyone has their own way of sitting on a bicycle. Everyone has their own way of driving a bicycle. So we all learn from our own adaptation, and so does a reinforcement learning agent. Yep. So the key intuitions over here are the cause, the effect, and the outcome. So for more or for easier understanding of students, we can just say that reinforcement learning is more like is more like a bot in a 3 cross 3 matrix. Let's consider a 3 cross 3 matrix, and it has to it has to go to a destination. It has to go to a destination where the destination's index are 3 comma 3. 3 comma 3. Let's just consider or visualize something called as a 3 cross 3 matrix. An agent or an AI agent is at 0 comma 1 block, and it has to go to 3 comma 3 block. What's the most optimal path of going to 3 cross 3 from 0? Sorry, of going to 3 comma 3 from 0 comma 1. So the optimal path is moving via the diagonal. Yes. Do you think that a reinforcement learning agent would take that optimal path all the time? It does not. A reinforcement learning agent does not take the optimal path each and every time. So it will just try and move around. It will just try and move around. It will just move from 0 comma 1 to 1 comma 1, or it could move to 1 comma 2, or it could move to 1 comma 3. So it will just somehow go based on the blocks and reach the destination. So each and every time it reaches the destination, it will just calculate the number of rewards that it has got. So whenever a reinforcement learning agent or an agent that learns from itself goes to the destination. Once it goes to the destination, it will just calculate how many rewards it got. So if the rewards are higher at one case and they are lower on the other case, agent will take the case where rewards are higher. Yes. And our agent does not need to go to the destination to calculate how many rewards it has gotten. So it can just calculate rewards based on each one of its step. Let's say it has moved from 0 comma 1 to 1 comma 2. It has moved from 0 comma 1 to 1 comma 2. It will just calculate the number of rewards that are placed on 1 comma 2 and other rewards that it has started with. Let's say it has started with 0 rewards, and when it comes to 1 comma 2, it has gotten 10 rewards. And these 10 rewards are the highest stake in the matrix. They are the highest number of rewards that the agent can get. So whenever whenever the agent starts getting more rewards, it will start exploiting the route. It will stop exploring and it will start exploiting. We'll understand what exploring and exploiting is. So exploring is a situation where agent just goes to all the cells of the matrix. It will go to each and every cell of the matrix and check whether what the reward is and what is the sum of the rewards that it is getting to take one path. It explores all the paths, all the possible paths. So when it is done with exploring all the possible paths, it will find one optimal path. Yeah, it will find one optimal path. And from the next time, agent will only be taking that one optimal path. So it won't be just exploring all the paths because it knows the most avoiding path or it knows the most rewarding part. So it won't just turn around from that path and start exploring. It will just exploit that path to get more and more rewards each and every time. So this is This is a condition where we can compare the concept called as exploring and exploiting. So when an agent has learned enough so that it has understood the whole environment and it has understood the whole situation, it will just start exploiting. Yep. So this is a very simple example with no changes in it. That matrix cannot change. It is fixed. It is 3 cross 3. In these situations, the agent can exploit. But there will be situations where exploiting is bad, or exploiting could just make the system bad. Yep. So we'll just see the situation where it could make things bad. So let us consider a situation where you are you are on a what do you call? Yep, you are on a plane race. You are on a race where you are supposed to drive an aeroplane. Okay, so the whole point over here is you have 9 checkpoints. You have 9 checkpoints, and you automate an agent, or you make an agent where you put rewards on each checkpoint. Yep, you put rewards on each and every checkpoint, which means reaching from one checkpoint to other. Reaching from one checkpoint to other will just give the agent a reward. So if an agent will think like a human does, it will just follow that path and get all the rewards. But you can't predict an agent. You can't predict an agent. You can't predict how it learns. Let's say it finds a loophole where it will just turn around the same checkpoint. It will just turn around the same checkpoint where it will end up getting more rewards than actually winning the race. So at the first checkpoint, let's say I'm giving 10 rewards. My agent will just start spinning around the same checkpoint for somewhere, let's say, 1,000 times. So 10 cross 1,000 is 10,000. So it will just get 10,000 rewards. But if it successfully completes the race, it will only get 1,000 rewards or 90 rewards or these sort of things. It will just get 90 rewards, 10 rewards per checkpoint. It will just get 90 rewards at the end of the race or by winning the race. But it has found a loophole where turning around the same checkpoint will give it more rewards. So as we just talked that agents are reward based and they could find loopholes. Yes, this is a loophole. What do you think will happen in that situation? What do you think happens when an agent finds a loophole and starts exploiting it instead of exploring? So this is the case that goes sideways. Whenever the agent starts exploiting, it does not think about the actual goal. So the actual goal for the agent is not to win the race. The actual goal is to get the most amount of rewards. Yes. So it is actually reaching its goal, but not in the way that we want. So in order to make those agents work in the way that we want, we have to put the rewards. We have to put the rewards, or we have to give the rewards on a basis or on an optimal path or an optimal setup. So these are the things that we need to consider. Yes, are we clear with that? So if you are clear with that, we'll just move to something called as Q learning. So this is the core concept. This is the core concept of reinforcement learning. We also call it as value-based learning. Yep. So in Q learning, conceptually, Q learning answers a very simple question. How useful is a particular action, or how useful is a particular situation? And the agent maintains values that represent how good an action has been in the past. So the agent maintains a Q table. It is also called as a memory system that stores actions and the rewards that the action has gotten it. So these values are not predefined, and they the agents learn gradually through experiences, as we just talked. And the agent does not know how the environment works. but it will just explore the whole environment and record each and everything in its queue table. So the queue table is just a collection of rewards, action and reward. Both together will make something called as a queue table. So the agent will explore each and every outcome and just start recording everything in a queue table. So it will just find or make up two things. One, learning values. Agent discovers which actions are vulnerable and which actions are valuable. So valuable. Valuable is a case where agent gets positive rewards or agent gets more rewards because of the situation. And vulnerable cases or vulnerable actions are cases where agent gets lesser rewards or negative rewards. Yes. So these are the two situations these are the two values that the agent learns based on the Q table. And the point over here is all these Q learning concepts or all these reinforcement learning concepts are experience based. So as the experience increases, the value improves. Yes, the optimal trial and error methods will always include higher experiences. Yep. Am I clear with that? So a good real world analogy. A good real world analogy is a simple battery optimization. Yeah. So we all know that we are not supposed to charge our phones when the phone is more than 80%. When the phone is charged more than 80%, you don't generally charge the phone until unless the battery is deteriorated. So and when the phone is less than 20%, I mean we don't let the phone fall less than 20%. So this is the optimal charge range where the phone performs better or where the phone's battery cycle is the best. So we learn from these things. The system learns which app consumes or which app consumes the more power and adjust usage policies accordingly. Yep. So whenever you see the settings app in your phone, you can see the battery usage or the power optimization that the system or the OS has just performed. So all these are examples of Q learning. Now we understood that Q learning stores something called as results based on experiences. Are we clear? Are we clear with Q learning? So in Q learning, there is one table where results and rewards are stored, and the decisions are taken based on the table or based on the previous experiences. Yep. So the whole process of Q learning summed up together looks like cause. Agent tries an action, it observes an outcome, and effect. It updates the value. It updates the value and estimates what the value could be for the next action in the state based on the previous values, based on the previous experiences. It will just estimate. It won't go in that way, but it will just estimate what will happen if it goes in that way because it has a memory of what has happened if it has gone in that way. And outcomes outcomes differ because of the memory it has. Higher value actions become preferred and lower valued actions are not preferred. So these are the processes or these are the core process of Q learning. Are we clear with that? So
Yes,
if you're
yes,
clear
sir.
with that, okay, we are clear with reinforcement learning and we are clear with Q learning. So we'll just have an activity. We'll just have an activity where we'll just consider a situation. We'll consider a situation of a room, a small room, not a big one, a small room with only single door. We just talked about vacuum yesterday, a vacuum based agent. Now I'm putting I'm putting two vacuum based agents in one room. So think of the outcomes that both of these vacuum robots would get you. So could they get you better results of cleaning the room faster, or could they just fight among each other? Could they just fight among each other to clean the floor faster? So I want you people to think of the most optimal way that both of these bots cleaning the room faster, and answer in the chat. Just answer in the chat. Just answer in the chat. What could the possible things be? So yeah, people, I'm just waiting for your answers. I'm looking at the chat right now. Both clean the room. So both clean the room in an efficient way. So what could that case be? Mr. Kanchi Manipal, what could that case be where they both don't fight with each other, or what could the case be? How do you set up an environment where they both clean the room? That's the point. That's the question. So we'll just take 2 minutes or 3 minutes of time. Try to brainstorm. Try to brainstorm a situation where two of these agents are left in a room with a similar goal of cleaning the room. And what is the most optimal path of cleaning the room? Just pick a pen and paper and draw a square. Draw a square with two circles in it. Try to place those circles in places or in optimal paths where both of the circles will cover the whole room. This is a very important activity so that we'll just understand how agents work. Agents work very similar to human brains. Agents work very similar to human brains. So we'll just use human brains and get all the outcomes that an agent could get. This is just a simple hands-on activity. We'll just take a couple of minutes, try to complete this so that we'll just understand how outcomes could be. So I'm making my own situation right now. As I'm making my own situation along with you people, just take a pen and paper. Through sensors, both sense each other and so both clean. So yeah, ma'am. So they both sense each other and they both clean. That's a situation where they both don't have the intelligence. They just have sensors right before them and they don't bump into each other. But in our case, both of the agents have intelligence like humans. What do humans generally do? We try to we try to do the task faster. So consider this metric. Consider this metric where both of them want to get more rewards and both of them just want to overrule each other to get more rewards. They are not friends or they are not something that just want to go with each other's plan. They make their own paths, they make their own thinking. So in this case, think what happens. Just think of situations that could happen. So my situation over here is I'll start both of the bots from a single corner. I'll start both of the bots from single corner and start driving those bots in the straight path. I'll start driving those bots in the same straight path, saying that this straight path is always good. So I'll just say that go straight and then go right, goes left and then go right in a way that I would form an S shape, multiple S shapes so that both of the bots cover the room. Both of the bots cover the room. This is my brain. This is what my brain has thought. I want you people, I want you people to make out the situations. So at the end of the activity, I'll just say why we are doing this. try to make out all the situations that you can and just type in the chat that what could the situations be. I have taken a situation where they just go in a straight way in an S shape, both to be clear. Okay. So I need situations from where to start and what happens. I'm just being clear. I need situations where the bot should start and where the bot should end, so that both of them find the most rewards or find the optimal path to get more rewards. Yes, just make out that situation. It's 7:16 right now. We'll take 4 more minutes and try to do this activity. While doing this activity, consider this slide. Consider the slide that is being showed on the screen. The agents should explore. The agents should explore the whole room. They should explore what's happening and what is going to happen. So consider this situation of exploration and exploitation together. And now try to make out the outcomes. Just try to make out the best outcomes. Okay, I've got a picture, yeah, from Kalavati ma'am. Let me just look into it. Yeah, ma'am. So you have started both of them from a random place and made a way, made a way so that they cover the whole room. That's that's great, ma'am. So that's a situation where both of them clean. So that's a great situation. But try to
Yes.
add rewards. Try to add rewards into the boxes, into the matrix boxes that
Okay.
you have just mentioned. Try to
Yeah.
add
Okay.
rewards like, yeah, ma'am.
Okay.
Just try to do that. The rewards should be random. They can't just be 0, 1, 2, 3, 4 numbers. They should be random as well as meaningful. Meaningful so that both of the bots take the most optimal way. That's a situation that we are supposed to consider. In the situation or in the picture that you gave, both of the bots are exploring. They're exploring the whole area. They're exploring each and every box. They are going on their own ways. And over here, they are not crossing their paths. We are just assuming that they don't cross paths. But when we involve, when we involve a situation called as multi-agent system, multi-agent system, we get a problem. We get a problem called as coordination challenges. Agents don't act like this. They don't act like an optimal bot, which do not cross their paths. They act as if they are mad. They act as if they are mad. They don't see the other bot or they don't see the other agent as if it's a learning factor. They just think that this thing, the other bot in the room wants to steal its rewards. It just wants to steal the rewards that this agent is getting. So that bot would just think in a situation where it will try to it will try to cross the other bot's way. So I'll just make the picture more clear, or we'll just understand the situation way better, way better. So draw one more box, and place 4 or 5 stars or as many stars as you want in a box. Yes. So just make one more box and place as many stars as you can like this. Just place. I've put off the blur. So just make as many stars as you can like this. So that so that each star seems like it's a reward. Each star should seem like it's a reward, or each star, for us, each star is a dust. So the star over there is equals to dust. The dust that the robot has to pick up. The dust that the robot has to pick up. and picking up each star or going to each star would give a plus one reward. Yes. So star is equals to dust and star is equals to plus one is what the agent should understand. Now consider leaving both of the bots where they can just see the star, nothing else. They can't see the matrix, they can't see the area, they can't see the room. All they can see is the star. All they can see is the dust or the star. So now make out a situation where both of the bots have to collect the dust. The goal is to collect all the dust in the room. The goal is to collect all sort of dust in the room. So now consider the path. Now start drawing the path. Firstly, we have started from assuming there are two bots in a room, and we just drew a box, or we just drew a situation where the agents or the robots have to clear the whole room or have to clean the whole room. Now we're in a situation where no. After that, we went to a situation where each and every corner or each and every box of the room is placed with a reward. Yes. First situation, no rewards. The goal was to explore the whole room. Yes. Second situation, we had rewards in place. We had rewards in place where, which means exploring the spot with more rewards is more better for the agent. Is more better for the agent. And this was third situation. Third situation where we involved a factor called as dust in it. What would that dust factor do? That dust factor would do something called as changing the situation. We change the situation getting from exploring and from getting rewards and to performing an action based on exploration, rewards, and then performing an action. That's how an AI agent would work. An AI agent would firstly perceive the environment and do actions, do actions based on the environment. And based on actions, it will just learn. It will just learn whether that action is good or not. Yes. So in order to learn if the action is good or not, we gave a metric called as reward. We gave a metric called as the reward. Now, those rewards are purely based on how many stars or how much dust each one of the agent would be picking. Yes. So in my situation, I have drawn this thing. I've drawn something like this. Those greens are the bots. Those greens are the bots, and those reds, the red colors are the rewards, and stars are the dust. I want you people to make out something like that. Something like that. So yeah, I've got one more picture in the chat where yeah, man. So sorry, give me a second. So yep. So now we have drawn something called as a decision tree. So we are not talking about decision trees now. We have talked about decision trees yesterday. So a decision tree, yeah, the okay, this decision tree makes sense. Yes, yes, yes. This makes sense where it tries to decide inside its brain. It tries to decide inside its brain based on the reward. Whether if a 10 reward is better or a 15 reward is better. You are considering a situation where the agent already knows. The agent already knows what are the rewards in the outside world. But in reality, in our situation, the agent does not know. The agent does not know what's the reward. So in this case, what is going to happen? It does not know anything about the environment. Neither does it know what is going to happen if it goes right or left, or if it takes the right path, or if it crosses the other agent's path. Our agent does not know anything technically. It will just explore everything. In that case, we can't just predefine rules. In decision trees, we can predefine rules, but in learning agents, we don't do something called as predefining rules. I'm just making this point clear. Now, we got a situation where both of them, both of the bots want to get the higher amount of rewards. They ha- they want to get the most higher amount of rewards, and one of the bot has figured out that crossing. Let's just consider both of the bots. We'll just give names to both of the bots. Uh, those names could be as simple as A and B. Those names could be as simple as A and B. And let's say bot A, bot A has found a star of dust. Bot A has found a star of dust and is has started moving towards the dust. Has started moving towards the dust. And bot B did not find any star or it did not find any dust. But bot B has some sense, has a bit of intelligence where it could just follow bot A. It could follow the other bot, so that it will somehow go faster. It will somehow go faster than the bot and take out the dust. That is right before bot A. Bot B overtakes bot A and just captures the dust that bot A was supposed to take. And it does. It does the same task for all the dust in the room. For all the dust in the room. So it is good for bot B. It is good for bot B where it is collecting all the rewards. It is getting the rewards from there, here, everywhere. It is just following bot A and getting the rewards. Now, in bot B's consideration, that situation is the most optimal one. It is not using any of its sense of finding the dust on its own. It is just following bot A. But in bot A's situation, it is perceiving the environment. It is perceiving the environment and thinking that I should go there, pick up the dust, and get my reward. But by the time it reaches, the dust, bot B has already taken. Bot B has already taken the dust. And what does bot A think? What does bot A or the agent A think? It'll just think that it'll just think that its perceiveness, the amount of perceiveness or the amount of thinking that it has got is bad. There's no dust over there, but still I saw some dust. But what is the reality over here? The reality over here is another agent, another bot that is powered by a powerful memory agent has just taken off the reward. So what will happen to bot A? What will happen to agent A or bot A? It will just get mad. It will just get mad, saying that its perceiveness has gone. So what is lacking over here? The only lacking thing over here is coordination. Both of the bots are not coordinating to each other. They're not working together for one goal. So this is what happens when when multiple AI agents are put together. They don't communicate with each other. They don't coordinate with each other, and hence form conflicts. Yes, and hence form lot of conflicts. So what are these conflicts? What are these conflicts? So one of the conflict that we got is bot B is taking off all the dust that bot A has been seeing or has been looking for, and bot A is getting mad. In turn, what is happening is bot B is not acting ethically. Bot B is not acting ethically, but as per the agent's thinking or as per the rules, as per the things that they follow, bot B is getting its rewards. It's not doing anything wrong. It's not doing anything wrong. So these are the challenges. These are the challenges that we face when multiple multiple agents are put together. So we just had this thing. We just had a discussion where both of the agents should work together, clean the room altogether without conflicting now. Yes, I gave a situation where they are conflicting. Now give me situations. Give me situations where both of them clean the room with coordination. How do you place the rewards? How do you place the rewards so that both of them just do the work on their own? Just think of those situations. Just think of those situations. In order to understand how AI agents work, we'll have to know how they think. So they think very similar to our brains, but they sum up all the situations, they sum up all the things, and then get to something called as perfection. It is not 100% perfect, but yeah, they are perfectly reliable. So now give me give me answers in the chat of what could the situations be, or what could the reverse situations be, where both of them work together without doing conflicts or without having any conflicts. Just give me examples. Let's see who has the best example. Let's see who has got the best solution where we could just clean the room or reach the goal without conflicting. So the time that we are having right now is to think, is to think of what could they think or what could the rewards system would be. Just think of it and drop your text or drop your ideas in the chat. I'll wait for one more minute and give you the most optimal solution. Collaboration gives equal rewards. So, okay, giving equal rewards when they collaborate with each other. So that's a great solution. That's a great solution. You say the bots that both of you collaborate together, and no matter what you get, there is no communication between bots. No, there is no communication between bots. I made it very clear that the AI agents do not communicate or do not share information. Yes. So without sharing information, they just perceive something called as rewards. Considering rewards, they'll have to shape their own intelligence. Now, you are a person who is seeing all the situations, all the things happening over here. So, how could you just change the environment or change the rules so that they could perform better? Is the question. The activity over here is you're you're the person or you're the god who wants to just change the environment or who has to just change the environment based on rewards so that the whole room is cleaned. I'm just stressing this thing so because this is very important. Multi-agent systems is a very important topic. So just try to get your own solutions. And yeah, so I'll just discuss one of the most optimal solution. So let's say, as agent two or bot two has got an intelligence where it is following bot one. I'll just say that I'll just say bot two that if you don't follow bot one, instead of following bot one and go in your own way, instead of following bot one and going in your own way, whenever you find dust or whenever you find something, you will be rewarded twice. You'll be rewarded twice than the reward that you have found following bot A. Now, what happens in this situation? As bot B thinks that it has to get more rewards compared to bot A, or it has to get rewards before bot A. That's the whole situation over here. So bot B wanted to get more rewards or faster rewards than bot A. So it started over maneuvering. It started over maneuvering bot A so that it will get more rewards. Now we are giving a situation to bot B where instead of just crossing its path, instead of just going around it, just go in your own way. just go in your own way. And whenever you find dust or whenever you find a star, I'll give you twice. You are getting one, you're getting 1 point when you were just following it, body. Instead, when you follow your own way and find a dust, I'll give you twice the rewards that you got from that path. So here the stakes have increased. Now bot B starts exploring. It starts exploring. Yes. Now the situation is optimal. Bot A follows its perceiveness. It perceives very well. It sees the dust, goes there, picks the dust. And bot B. Bot B does not follow bot A enough. Bot A also starts perceiving its own things. It starts perceiving the environment and tries to get at least one particle of dust. Here, what we are achieving is we are achieving coordination among both of them without actual communication. There is no actual communication between both of the pods, but we have coordination. We have coordination because we change the environment. We change the environment where each reward of bot B, each reward of bot B is twice as bot 1 or bot A. Yes, clear with this? I hope you're clear with this. We'll move to something called as adaptive. If you're clear with this, we will move to a demo of adaptive traffic signal. Yes, if you're clear with multi-agents, we'll move to something called as adaptive traffic signal.
Okay, sir.
Yeah. So what happens in adaptive traffic signal control system? So firstly, the cameras. The cameras observe the traffic and they observe the traffic. They think about where the heavy traffic is, on which lane is there, are there many vehicles, or in which lane there are less vehicles. So it just perceives them and adjusts. It adjusts signal timings. It adjusts signal timings, and based on signal timings, there is an action. There is an action going on here, which leads to letting the traffic go. Based on the traffic density, the agent adjusts signal timings, and based on perceivedness and decision, we have an action, which is letting the traffic go. So doing these three things again and again, we get to a path, we get to a situation where we get the optimal pattern of doing this, all these three things all together. Yes. So this is how adaptive traffic signal control works. Now we'll just have, we'll just see a demo. We'll just see a demo on how these things work. I'll just show you a piece of Python code. I'll just show you a piece of Python code. So it is a tiny optimal improvement skill. Yes, it's a more improvement skill sort of thing. I'll just run it in Google Colab. I'll just run it in Google Colab. So let me just open Google Colab. Yeah, I've opened Google Colab. And we'll just understand why I have written this code. Firstly, we talked something about Q learning. So this is just a demo of how Q learning works. Yes, based on the traffic signal and based on Q learning, we'll just see how they work in real time. Okay. So firstly, we just gave two states, one as low and one as high. So one is low traffic and one is high traffic. And actions that we gave are extended green and switch signal. Yes, extended green and switch signal are the actions that the agent would be taking. Now we just define rewards and actions. We define a function for divide, a reward, and a function for action. Okay, and right below the functions, we wrote a predefined rule. We wrote a predefined rule or a for loop or a for loop. This is a very simple syntax. This is a very simple syntax of what is going to happen and when this happens, what should be the thing. So we got an output of from step 1 to step 20. So we'll just look at the outputs. The outputs that we got over here are traffic state low. So as the traffic state is low, it has chosen an action. It has chosen an action where it will just let the traffic go, extend the green light, which is letting the traffic grow. So this is step 1 or state 1. Next step. So next step is also low, and the third step is also low. Now, in these three states, the traffic is low. So this is not the situation on each and every time. So when it comes to step 4, the traffic is high. So the traffic is high, and what has happened? The traffic is high. When the traffic is high, we extend the green again because why? Right on step 3, right on step 3, we switch the signal. We switch the signal from green to red, and because of this decision, because of this decision of switching signal, the traffic has become into a high state, and our agent will just understand that this state is not good. The traffic is being high. So I would just rather choose green and extend the green. Yes. And as soon as the traffic is low, as soon as the traffic is low, we we just switch the signal to red and vice versa. So whenever the traffic is high, we'll just switch the signal to green, letting all the bikes and cars to go. And whenever the traffic is whenever the traffic is low, we'll just put on the red light, allowing the other lanes to go. So this is how environment based agents would take decisions. So I have simulated till step 20, and you can just simulate any number of situations based on the condition that you give in here. So I'll just give 60 and rerun. I save the code, and then I'll just rerun. So if you can see, we got 60 different situations or 60 different steps. So this is how this is how an AI agent would just act based on state and choose the action, and based on state and action, it will get a reward. Yes, based on state and action, it will get a reward. If you just see, if you just see, if you just see the rewards, look at this. The reward has started from -2 and it has gone to +3, and from +3 it has gone to +5 and +5 again. So why is it getting 5 and why it is getting 3? It is getting 3 in a situation where it is switching the signal. It is switching the signal to red, and it is getting lesser rewards. Why? Because switching the signal to red is making a situation where the traffic is becoming heavy. So heavy traffic is not good, is what it has learned. And whenever there is heavy traffic, in order to get more reward, it will just switch the route or the color to green. So this is how an AI agent would think. Okay, are we clear with that? So if you are clear with that, we just we just understood how reinforcement learning works. Yeah. So we just understood how reinforcement learning works and how do AI agents think. How do AI agents think? And based on the thinking, how do they relearn? How do they relearn based on the decisions and based on the rewards? This is what we have learned. Summing up the whole session, we covered something called as reinforcement learning. Yes, we just firstly we saw why rule-based agents fail. After that, we just know, or we just understood what learning agents are. After that, we moved to something called as adaptive agents. After adaptive agents, we we just saw what was reinforcement learning. We did a hands-on demo on reinforcement learning. And after reinforcement learning, we understood what Q learning is and how what are Q values and Q table. These are the concepts that we covered in both of these. And after that, we talked about something called as exploitation and exploration. Exploitation and exploration are the topics that were dealt by giving a demo of two bots or two vacuum bots cleaning a room. And we got a challenge while we were dealing with two bots. That challenge is what the real world multi-agent systems would face. The real world multi-agent systems would face. And after this, after this, we just saw what could happen. What could happen if the traffic signals worked based on learning agents. Yes, the code demo that we just saw is a live example of if what could happen if traffic signals would work on learning agents. This is what we have learned in this session. Yes, and if you people have any questions regarding the session, or if you people have any questions regarding the topics that we covered, we have the last 12 minutes for it. And right before the questions, I just want to put a point. I just want to make up a point. So the point is tomorrow we'll be learning, or you people will be learning on how to build AI agents based on low code or no code. Based on low code or no code. We'll try our level best to do something with no code. So in order to do those hands-on sessions, in order to do those hands-on sessions, right with the speaker, you will have to have a prerequisite called as Node.js. So I hope your people know what Node.js is. It's just a JavaScript language. So please download Node.js in your systems so that you will just able to follow and you'll just able to follow and do things with the speaker. So yeah, sir. So please give me more examples on exploitation on image processing, sir. So based on image processing, exploration and exploitation. Okay. So let's say uh, our general CNN algorithm, it processes images based on pixels. Yes. So whenever an algorithm has found a way of getting more pixels together. It found an optimal way of finding or processing more pixels together. It will start exploring. It will start exploiting. Sorry. It will start exploiting that one method. And because of this exploiting, it will stop the whole concept of reading all the pixels together, reading all the pixels together, and hence not processing the image properly. So in order to process the image properly, it has to explore the whole image. It has to explore the whole image so that it will just get each and every pixel right. It will just process each and every pixel right. So this is one example. It is just one example so that you can use exploration and exploitation, or you can understand exploration or exploitation when it comes to image processing. And adding on to this, exploring each and every pixel is not very optimal. Exploring each and every pixel is not very optimal. So that's why CNL algorithms are not learning algorithms. They are processing algorithms. So that's the core difference between predefined processing algorithms and learning agents and learning algorithms. I hope I was able to answer your question, sir. Any more questions? Yeah.
So if you have any questions, any queries?
And also take 10 minutes of time after the session and try to think of the situation that we just talked about. We just talked about the bots, right? So try to make out the most optimal solution out of it. Okay? If you don't have any queries. Yeah, sir. Thank you.
So can you please provide the code what you have shown?
Sure, man. I'll
So
just paste the code. I'll just paste the code in the chat if it's okay. Yep.
yes, sir.
I've
I'll
pasted
copy
the
it and
code.
I'll send it. Yes, sir.
I've pasted the code in the chat, man.
Okay, sir.
And if anyone wants to just explore how low code or no code agents are done, tomorrow's session will be about flow wise. So yeah, I've got a question. Sorry. As educators and researchers, how should we prepare students for future where AI agents are integrated into more industries? So yeah, sir. Sorry, ma'am. So for your question, so we need to prepare or we need to say to students that there's this myth or there's this taboo where each and every one of us or anyone in the world is saying that AI is going to eat or AI is going to take your jobs. So I'll just say it in this sense based on this question. So AI is not really going to take our jobs. AI is not really going to replace software engineers. It is just going to help. It is just going to help us software engineers or us as researchers. It will be just helping. It will just help to make our jobs better. So as AI agents are integrated in most of the industries, the students need to know how to use those agents. They need to know how to use those agents and how those agents work internally. Both of these factors would just make sure that it will be easier for them to get into those industries and work efficiently with the industry standards. Yeah, sir. So I'll just provide the PPT. Don't worry, sir. I'll just put the PDF to Neela ma'am so that she'll just send it to you. Any more, any more questions or any more doubts? Okay, for yesterday's session also, sure, ma'am. I'll do that.
So once
I just send.
sir shares, I'll post that in the group.
Both of the PDFs are downloading right now. Just so give me a couple of minutes, so I'll just send them. Learning
So all of
agents
you,
done.
please switch on your cameras and you can just contact sir. You can switch on the cameras. I request everyone, please switch on the cameras. Harsha sir, I request you please switch
Yeah,
on the
sure.
camera.
Okay. Give me a second. The camera is
Sirisha
malfunctioning.
ma'am,
I don't know why. Uh, I guess there's a glitch with my camera, ma'am. I'm just not able to switch it on.
okay, sir, no
Let me
problem.
just check it again.
Yeah, we'll wait for 2 more minutes, sir. Then we can have a group picture.
Yeah, sure. Or else I'll just leave the call, get back so that I'll just
Sure.
get off this
Okay, sir.
glitch.
Okay, sir. Okay, sir. I have shared the feedback form in both YouTube link and also in the chat. All of you, please check and fill the feedback form.
Yep. So I've got a question. Yeah. So I'll just, sir, 2 days back, I heard about that around 32,000 bots are generated without human intervention and discussing about humans. I feel that this is a very scary thing. How will it affect us in future if they create bots themselves without human control? So, yeah, sir. So, am I audible? Ma'am, am I audible?
Yes, sir, you are audible.
So,
Sir,
my camera is not working. I thought my mic is also not working. So, yeah.
No
So, I'll just be
problem, sir.
answering your question, sir. I'll just answer your question. So, we don't need to worry about bots creating uh, their own things like chatting between each other, or they just let's say forming an environment. As long as bots are inside the rules, as long as bots are inside the rules, it is all great. We are not going to see any apocalypse as long as we put some rules or we put some boundaries to the bots. So I know it looks scary where they are just talking to each other without any human intervention. But yeah, it won't really affect us because we don't live inside the computer, but the bots do. They can't just get outside the computer or they can't just get outside our screens, or neither can they just get outside the internet. They can't really affect us personally. But yeah, there could be chances in near future where one where they could just be they could just be the better side of us in the internet. They're already better. GPT is way better than us when it comes to knowledge, and when it comes to verifying things, Grok is better than us in verifying things. So agents, AI agents or chatbots or any AI models are better than us in one sense because they have a lot of knowledge than we do, but they don't have one thing, which is intelligence of their own. But yeah, that's all I got to say. So we don't really need to be scared because they are more intelligent than us or they have more knowledge than us. But I can just reassure you that there will be no situation where they could just take over things on their own as long as they are inside the rule bounds or as long as they act inside the rules that they were defined in. Yep. I hope I've answered your question or I've just added something that would reassure that it you won't be scared or you won't be worried about the situation. And both of the PDFs are downloaded and just dropping it to ma'am so that you people can get it. Learning autonomous behavior, AI agents, and agent exchange. Yeah, ma'am, I've sent it. I've sent both of the PDFs to you in WhatsApp. You can just send it to all these faculty members. Yeah. So if you don't have any queries, any more queries, we can just end the session. Sorry. And as a note, leaving note, I just want you people to download Node.js in your laptops tomorrow so that you can just follow what the speaker would be doing, or you can just follow him and do with him. Yeah, thank you everyone for the time you have given or the time that you have put, the effort you have put, the 1.5 hour. Thank you for giving this time to me. Thank you, man.
Sir, what to download?
Node.js, sir. I'll just put the link. I'll just type it in the chat. Node.js. If you want, I'll just give the download link to you. I've also dropped the download link for Node.js. I've dropped the link for Node.js so that you people can just download it from there.